Hello everyone, in this video we shall be deriving the expressions for electric potential and electrostatic potential energy. As we know, when we move a charge between two given points, some amount of work is to be done. Now when we bring a charge from infinity to a point, the amount of work that will be done per unit charge will be known as the electric potential at that point. The amount of work done in bringing a unit positive charge from infinity to a point is the electric potential at that point. Now for bringing a unit charge, that means let's say for 1 coulomb of charge, the work done will be equal to the potential. Now if we bring q coulombs of charge instead of 1 coulomb charge, the total work that will be done will simply be q times v. This is the expression for work done in bringing a charge from infinity to a point, and this work done will be stored up inside the system as electrostatic potential energy. Now in this slide, we shall be deriving the expression for electric potential. Expression for electric potential at a point due to a point charge. Suppose there is this point charge capital Q at the point O, and we intend to measure the electric potential at the point P, which is at a distance r from the charge capital Q. Now in order to measure the electric potential at point P, we bring a unit positive charge from infinity to P. That means from infinity we bring a unit positive charge in this direction. Okay, now we'll assume that at a certain instant of time, the unit positive charge is at a point A, which is at a distance x from P. Now I'll be showing it on the diagram. While bringing the 1 coulomb charge or the unit positive charge at a certain instant of time, it arrives at the point A, which is at a distance x from the point P. From the charge Q, from the point O. So I'll just correct it on the diagram. So from the charge capital Q, the unit positive charge is at the point A. Now at this point, there will be a Coulomb force acting between the test charge or the unit charge and the charge capital Q. So we'll write the force between the charge capital Q and the unit positive charge is given by F is equal to 1 by 4 pi epsilon naught product of the charges, which is capital Q and unit charge, that is 1, divided by the square of the distance, which is x square. Now this force is repulsive in nature because both the charges are taken to be positive. That means the direction of the force will be in this direction. That means as the unit positive charge moves towards the point P, a work is required to be done continuously against the electrostatic force of repulsion between the two charges. Now if we want to bring the charge from the point A to the point P, which is separated by a distance dx, then the work done in this process will be given by work done in moving the charge from A to B, which is being separated by a distance dx, will be dw, because if the displacement is infinitesimally small, the work done should also be infinitesimally small, which is equal to F times dx. Now here we are doing work against the force, so there will be a negative sign. So total work done in moving the charge from infinity to the point P will be W, which is integral of dw, and dw is your minus of f of dx. Now f is a function of x as given by this relation, so we'll just have to substitute f as 1 by 4 pi epsilon naught q by x square. So w is equal to minus 1 by 4 pi epsilon naught q by x square dx. Now the limit of integration will be from infinity to r, because we are starting to move the unit positive charge from infinity and we are stopping at a point which is at a distance r from the charge capital Q. Now 1 by 4 pi epsilon naught is a constant and so is Q, so it will come out of the integration. So it will be dx by x square. Now here we shall be using the formula x to the power n is integration of x to the power n dx, integration of x to the power n dx is x to the power n plus 1 by n plus 1. So here the value of n is minus 2. So q minus q by 4 pi epsilon naught x to the power minus 2 plus 1 divided by minus 2 plus 1. The limits being from infinity to r, minus q by 4 pi epsilon naught, which will give me minus 1 by x. So from here I can cancel out the two minus signs. Now I need to substitute the higher limit and the lower limit in place of x. So work done is q by 4 pi epsilon naught. First in place of x I shall substitute r, So it will be 1 by r minus 1 by infinity. 1 by infinity will give you 0. So this is the total work done in bringing a unit positive charge from infinity to a point. And how do we define the work done in bringing a unit positive charge from infinity to a point? It is defined as the potential. So potential for a point charge q at a distance r is given by this particular expression, that is V is equal to q by 4 pi epsilon naught r. The SI unit of potential is volts and it is always a scalar quantity. This is the expression for electric potential. Now for finding out the expression for electrostatic potential energy, you just need to use the formula W is equal to Q times V, because from infinity, instead of 1 coulomb charge, we may also bring a small q coulomb of charge as well. So what will be the work done in that process? So we already know that work done in bringing a unit positive charge from infinity to a point is given by 1 by 4 pi epsilon naught q by r, which is your electric potential. That multiplied by the total charge which we are bringing will give you the electrostatic potential energy of the system. So this work done is stored up inside the system as electrostatic potential energy, and you may also call it as the energy required to construct a system of charges. Now this expression can be used for solving various numericals. For example, three charges Q1, Q2 and Q3 are located on the three vertices of an equilateral triangle. So what will be the total potential energy of the system? Or the question may be put in this way: what will be the energy spent to construct this system? So here you just need to calculate the electrostatic potential energy between the three charges Q1, Q2 and Q3. So how many terms of potential energy will be there? There will be term between Q1 and Q2, there will be a term between Q2 and Q3, and also there will be a term for Q3 and Q1. So the total work done, or the potential energy, which is also denoted as U, will be given by 1 by 4 pi epsilon naught Q1 Q2 by R plus 1 by 4 pi epsilon naught Q2 Q3 by R plus 1 by 4 pi epsilon naught Q3 Q1 by R. Now you may get another type of numerical where they will say four charges are located at the vertices of a square, each of side A. So again, you will have to calculate the electrostatic potential energy between two charges separately and then add it together. Altogether, there will be 6 terms of potential energy. With that being said, I would like to close this video. I hope you have enjoyed. Stay tuned for more videos coming up on this channel. Thank you.